Hi there! So far, in the Electrical Engineering Fundamentals series, we have talked about the basic concepts of electricity, the current, the voltage, and the power. Today, we will talk about one last basic concept before we dive in the analysis of electric circuits themselves. We will talk about conductors, insulators, and semiconductors. How do we define them, and how we distinguish them? Unfortunately, this is not an easy subject. If we wanted to be exhaustive on it, we would need to dive into chemistry and quantum physics. However, I will try to remain as simple as possible and give very high-level information that will make you understand the differences among these materials without using any math concepts. So, let's begin. We are all accustomed to electric wires, and we all know that they are usually made of copper, although sometimes other metals are used for them. We know that all metal, more or less, are capable of conducting electricity, so we call them conductors. We are also accustomed to insulators as the plastic material that covers the wires, and by extension we know all that plastic and rubbers make good insulators. Also other materials, like glass and paper, are insulators. However, some materials are better insulators than others. Some are able to insulate just a few volts of electricity, while others can withstand thousands of volts. Many people interested in electronics also know what semiconductors are, or at least they know that the material used to make transistors, diodes, and integrated circuits are some sort of semiconductors. But what really are those materials? How do we draw a line between each material and put them in one category or another? Is water a conductor or an insulator? What about paper? Does it really protect against electricity? And metals? Are they really all conductors? Why don't we use less expensive metals instead of copper to make wires? Couldn't we use iron instead? To answer all these questions, we need to look inside the materials. Let me make a disclaimer at this point. What I'm about to say is a wild simplification of how things are working within an atom. In this context, I'm even using proper words to describe how things are working, but I am choosing simplicity over rigor. No need to have a master in particle physics or in material science to follow this video. Matter is made of tiny particles named atoms, and atoms are made of even small particles named protons, neutrons, and electrons. Protons and neutrons reside at the center of the atom structure that is called the nucleus. Electrons are allocated all around the nucleus at a long distance from it, relatively to the scale of the nucleus itself. Electrons also move around the nucleus following certain patterns which we call orbitals. Different orbitals are at different distances from the nucleus and have different shapes. Electrons inside the orbitals have a certain amount of energy, and that energy puts them in a different position in the orbital, which we call levels. Depending on the amount of energy the electrons possess, they are located closer or farther away from the nucleus. The more energy, the farther they are. The most external orbital contains at the most external levels what are called the valence band and the conduction band. The valence band contains those electrons that allow atoms to group together to make molecules. The conduction band contains those electrons that allow the material to conduct an electrical current. In conductors, the conduction band has always one or more electrons in it. In insulators, the conduction band is totally empty. Here is a picture that better describes what we have said so far. For conductors, you see that the valence and conduction bands are overlapping. This means that some of the electrons in the valence band are also occupying the conduction band. For that reason, conductor atoms have always at least one electron in the conduction band. These electrons are very free to move, and so they can be used to generate electrical current. For insulators, the valence and the conduction bands are far away from each other, and the conduction band is therefore empty. The gap between the two bands is so high that it is almost impossible for an electron to move from the valence band to the conduction band. This is the reason why insulators cannot conduct current. But of course, if we apply a voltage high enough, we can still provide the electrons with enough energy to jump from the valence band to the conduction band. However, in that case, because of the very high voltage, electrons jump from one band to the other in a disruptive way, causing the material to break. Once that happened, the insulator loses its property and is no good anymore as such. And finally, in the materials called semiconductors, the valence band and the conduction band are separated, but they are close to each other than in the case of insulators. Because of the gap, the conduction band is empty and the electrons occupy only the valence band. However, since the two bands are so close to each other, it is relatively easy to provide enough energy to some electrons to jump from the valence band to the conduction band, in which case we can have a current, although not strong enough as in the conductors. This peculiarity in behavior of the semiconductors is what is exploited to make most of the electronic components, like the transistors, diodes, integrated circuits, and so forth. And because these components are made out of semiconductor materials, they are generically all called semiconductors themselves. In this video, we have talked about energy bands in materials and how materials behave based on the position of the two highest energy band levels. We have said that conductors are those where valence and conduction bands are partially overlapping. Conversely, insulators are those that have a high gap in between the valence and the conductor bands. And finally, semiconductors are those somewhat in between. I really hope you liked this video and made some sense out of it. Please do not forget to give me a thumbs up and to subscribe for free to my channel if you haven't done that already. See you on my next video, and as usual, happy experiments!